Hello YouTube, welcome back. This is Unit 4, Section 2 of our Introduction to Calculus at the end of Pre-Calculus Honors. What is the first derivative test? Alright, so let's take a look at this in Sage. We already looked at this in the T84. Let's say this is, your name and the date. What was the date? Doing this quite a bit later. 5/13. Okay. So the date is 2019.05/13. Right? Yeah. And what are we doing here? Unit 402. The first and the second derivative test, I guess. First and second derivative tests. Aha. There you go. Alrighty. So the first thing we're going to do is let's create a function, a polynomial function. Let's say f of x is, let's say something silly. Let's say x minus 1 times x minus 2 times x minus 3 times x minus 4 times x minus 5. Okay. So x minus 1 times x minus 2 times x minus 3, times x minus 4 is fine. Make this a little bit smaller. Let's just do that. Okay, so let's show that. And if you evaluate that, you get this crazy function. All right, but what if you wanted it all expanded out? Okay, so how about we say show expand f of x? Let's see what that looks like. And you get you should get a fourth degree polynomial in standard form. There it is. All right. Now let's say we let g of x equal the derivative of that. Whoops. And then we show the derivative. Now, based on the power rule, did you expect this? Well, no. We want to expand that also. In expanded standard form, all right, so let's see. The derivative of x to the fourth is 4x cubed. The derivative of 10x cubed is negative 10x cubed is negative 30x squared. The derivative of 35x squared is 70x. The derivative of negative 50x is negative 50. The derivative of 24 is 0. That's good. But what I'm interested in is what the graphs look like. So let's plot f of x. Let's just do f of x. Now I want to see all the zeros. There's a 0 at 1, 2, 3, and 4. So how about we go from 0 to 5 for x min and x max and see what that looks like. Alright, so we have a 0 at 1, a 0 at 2, a 0 at 3, and a 0 at 4. What I'm getting at, though, is the first derivative test will show you that there's a min here where the derivative changes in sign from negative to positive, and a max here where the derivative changes in sign from positive to negative, and a min here where the first derivative changes in sign from negative to positive. And how are we going to see that? Let's graph the derivative in the same window. So if we want to graph more than one function on the same set of axes, we have to make a list with square brackets, list the two functions. So now we know which is which. All right, the blue one, or cyan, whatever that color is f of x. G of x is sort of green. All right, just a moment. Sorry, I can't see my notes. All right, so like we said, where the derivative is 0, the green curve has a 0 here. There's a min in the original curve, the cyan curve, f of x, because we have negative y values for the green curve and then positive y values for the green curve. So the derivative is changing from negative to positive. So the tangent line slopes are going down, then horizontal, then going up. All right. Likewise here, the blue curve has a max, excuse me, here because it's a 0 on the green curve, where the green curve is going from positive to negative, so the slopes of the tangent line along the blue curve are going from increasing to decreasing. All right. The slopes are the tangent lines are increasing to decreasing, and likewise for this min over here. For fun, what if we throw in the second derivative? Let's call that h. Okay, so how about h of x is the diff of g of x, which is the first derivative, so we'll get the second derivative. And let's show what we get algebraically for h of x. Before the plot. And again, we should expand that so we can see that it's a polynomial. There it is. And then let's plot it. Let's plot h of x in here too. So not the blue, not the cyan, not the green. What was that, magenta? Now notice here where you have a critical point or a 0 for the derivative, right? Where the green curve has a 0. If the second derivative is positive, it's going to look sort of like a smile parabola there at the relative min. Okay, so that's a second derivative test. Now where is the next 0 for the derivative, the green curve? Here it is. Notice there the what is this, magenta curve, the second derivative is negative, so it's going to look like a frown parabola there for relative max when the derivatives change from positive to negative, right? The critical point. We can find the critical point is the zeros of h or f prime. And likewise, the other 0 of x of the green curve, and the derivative, right? That's f prime, g of x, is where we have a min for f of x, the cyan curve, because we're going from negative derivatives to positive derivatives. That's the first derivative test. But the second derivative test says also if you have a critical point for f prime where it's 0 undefined, where it can change sign, and the second derivative is positive, it's got to be a min because it's going to look like concave up at a critical point. It's going to look like a smile parabola. And there you go. That's exactly it. And if you want, you could also say, how about solve for the zeros. Whoops. I'm not going to solve for the zeros of f of x because they're obvious, right? They're at 1, 2, 3, 4. I did that on purpose. But if you solve for the zeros, let's do a show solve. Show solve for the zeros of g of x, which is f prime, the first derivative, not h of x, f double prime, the second derivative. And we're solving with respect to x. Let's see what we get for the zeros of h of x. I should probably put, no, not h, I want g. All right, so you know what? Let me put this with the g stuff right after we print out g. So it's right after we print out g. Let's do that. Oh, and I'm solving an equation when g of x equals 0. Remember in Sage, equals is a Boolean. It's either true or false. The solve command tries to figure out what x values make the statement true. And so what are the zeros of g of x? Alrighty. Well, one of them is 5 halves, 2.5. That's easy. And then we have these complex conjugate pairs. No, they're not complex conjugates, but it's 5 halves minus 1 half rad 2 and 5 halves plus 1 half rad 2. And so 2.5, huh? So one of the zeros of the green curve is 2.5 right there. That's f prime, the green curve. The other 0 is 2.5 minus half of rad 5, and this one's plus half of rad 5. If you want the, let's see, if you want to actually see those numbers, what you got to realize is that the answer here is in square brackets, so it's an array or a list. So the first answer is sub 0, sub 1, sub 2. So we want to see the decimal representation of the first answer. We got to say sub 0, Let's take a look at that. But that's an equation. I don't want the equation, I want the number, so dot the right-hand side of that equation. And then we want the numerical version, you know, the decimal version of that. So how about dot n? So it's about 1.38. 1.381 there. That's what that is. So a little bit to the left of 2.5 and the same distance to the right apparently of 2.5. So how about if I write, let's print out the decimal version of all three of those roots. Because the second derivative is a cubic, we've got 3 roots, since f was at 4th degree. And the second derivative will be a 2nd degree, right? So as we got, right? There it is. All right, so let me copy this. Well, my mouse is not cooperating. Come on, mouse. What I'm going to do is I'm going to do this 3 times, but I'm going to print out sub 1 and sub 2. So you get all the decimal roots of f prime, the critical points of f prime, where f prime is 0 undefined. So 1.38, 3.618, 1.381-ish, 1.382-ish, I guess, 3.618-ish, and 2.5. 3.618-ish, I guess, is this 0 for the green curve here. Okay. All right, so that's just a demonstration of the first and second derivative test. I hope that was helpful. Enjoy your homework. Where is it? We're on page 198, multiples of 5. Okay. Have a nice day, YouTube. Bye-bye.